Hello everyone and welcome to Robot Operating System version 2 Jazzy Jalisco tutorials. In this tutorial, we explain how to implement from scratch a feedback control algorithm and a Python code for controlling the position of a mobile robot in the two-dimensional space. Namely, the goal is to steer the robot from some initial position to some desired position specified by coordinates in the two-dimensional space. Here for illustration, we are controlling this blue differential drive mobile robot. And let's immediately illustrate and demonstrate the performance of the control algorithm. Now, I'm running the control algorithm and the goal is to steer the robot to the position over here. Here you can see the time and X and Y positions of the robot as well as the orientation angle theta. And over here you can see how the pose of the robot is changing over time. You can see how this arrow is moving. This means that the robot is moving to the appropriate position. The end position is 10-10. Here we have deliberately decreased the proportional gain of the controller in order not to make the controller to run too fast and such that you can see the motion of the robot. To simulate the robot motion, we are using the Gazebo simulation environment shown over here. Here is the Python code that's used to control the robot motion and that implements the controller. As you can see over here, we have implemented a class that embeds the controller. That is, we are using the object-oriented approach to implement the control algorithm. In this video tutorial, we thoroughly explain how to write this program from scratch and how to write the complete ROS2 package for controlling the robot motion. Also, we have created an additional manual shown over here explaining the basics of the position controller. This manual contains text description, formulas, and all the details of the position controller. In addition to this, we have created a detailed manual explaining all the steps that you need to perform in order to implement the material presented in this video tutorial. This manual explains all the commands, their meaning, and the basics of ROS2. Links to all the files explained in this video tutorial, that is the links to the Python code, ROS2 package, and these two manuals are given in the description below this video tutorial as well as in the comment section below. Okay, let's start with explanations. First of all, let's look at the big picture and let's briefly explain what you will learn in this video tutorial and the basic principle of a feedback control algorithm. Consider this figure. This figure shows an illustration of a 2D mobile robot. Here is the robot body. Here is the left wheel and the right wheel. The left and right wheels can spin, and by changing the velocity of these two wheels, that is by changing the RPMs of these two wheels, we can control the position and orientation of this robot. The goal is to steer the robot to the desired position specified by the point D. The coordinates of the point B are selected by the user. Here, the point B represents the center of the robot body. That is to say, our goal is to steer the point B from some initial position to the desired position represented by the point D. Let's talk a little bit about controller, and later on we are going to thoroughly explain the kinematics on this figure, and we are going to explain the working principle of the robot control algorithm. The controller receives a robot position and robot orientation from a sensor and calculates the linear and angular velocities for controlling the robot motion. That is, we assume that there is a sensor measuring the position and orientation of the robot body. When we say position, we actually mean the coordinates of the point B. That is, we can assign some fixed coordinate system, for example, the coordinate system with the origin O shown over here, And we can safely assume that there is a sensor measuring the coordinates of the point B, that is to say, measuring x and y in this coordinate system. And we assume that this information is available for feedback control. In addition to this, we assume that robot orientation can be measured. The robot orientation is represented by this angle theta of t, where t is time. That is, we assume that we can measure the angle of rotation of the robot body with respect to the horizontal axis x. That is to say, by using x, y, and theta, the control algorithm should steer the robot from some initial position to the desired position d. The idea over here is to calculate the desired command velocities. So when we say command velocities, these are the linear velocities, that is this velocity vb, and the angular velocity that tells how the robot should rotate around the axis associated with the point B and directed toward us. That is the angular rotation velocity of this robot. To summarize, we are controlling the linear velocity, that is, we are controlling the velocity vb, and we are controlling theta dot, that is, we are controlling the rotational velocity of the robot around the point B. These calculated values of the linear and angular velocities are sent to the local motion controller or the local differential drive controller. These values are actually set point values for the local motion controller. That is, the local motion controller should control the left and right wheels of the robot such that the robot position and orientation follow the set point values. In this video tutorial, we are not going to implement a differential drive controller. We are just going to use a plugin, that is, we are going to use a piece of program developed by someone else to control the robot wheels. What we are going to calculate is VB and theta dot. The measured robot position and orientation are components of an odometry message. The full odometry message consists of robot position, robot orientation, robot linear velocity, and robot angular velocity. However, in this tutorial, for feedback control, we only use the position and orientation. In particular, in this tutorial, we explain how to implement a Python class that embeds, number 1, a ROS2 subscriber object for receiving the robot odometry information from a sensor. The subscriber uses a callback function to read and process the odometry information. This callback function is activated every time there is a sensor data on a ROS2 sensor topic. The callback function adds a feedback loop to the system. Then we will implement a ROS2 publisher object for sending the control velocity commands to the robot. The ROS2 publisher object uses a timer with a defined control period for calling a controller function. The controller function calculates and sends the control velocities to the Gazebo local motion controller or differential drive controller, which moves the robot. Besides this, we explain how to establish a communication link between a ROS2 program and a Gazebo simulation of a differential drive robot. The main motivation for learning the material presented in this tutorial comes from the fact that all the implementation steps explained in this tutorial are the implementation steps that you will have to perform on a real robot. That is, to control a mobile robot, you will need to write a Python code that will read sensor information and that will send control commands. Later on, you can modify the code files presented in this tutorial and adapt them to a specific robotics application. In the tutorial, we use a differential drive robot Gazebo model that comes with the Gazebo simulation demo package. That is, in the tutorial, we do not explain how to model a differential drive robot in Gazebo and ROS2 from scratch. If you're interested in learning how to model a differential drive robot, we created a number of tutorials explaining how to model a differential drive robot from scratch in ROS2 and Gazebo. Simply go to the YouTube page and search for ROS2 and Gazebo differential drive robot Jazzy Jalisco, and there are several tutorials. Before we proceed with further explanations, here's the license and the copyright notice. This document develops code files, lesson video, and all the provided material are referred to as the learning material. The learning material is the ownership and the original work of Dr. Alexander Haber, who is referred to as the author in the sequel. You have the right to use the learning material for personal educational use and strictly for non-commercial use. The learning material should not be copied, redistributed, or publicly posted on public or private websites, code repositories, and social media platforms. The learning material should not be reproduced manually or automatically using an algorithm or an AI model from this video and then posted on public or private online repositories. Unless allowed by the author, the learning material should not be used as lecture material on online learning platforms and in university courses. Unless allowed by the author, the learning material should not be used to organize courses for training engineers working in companies or paid academic researchers, such as paid students, paid postdocs, paid professors, etc. The provided code files and learning material should not be used to train an AI algorithm or a large language model. And finally, unless allowed by the author, the learning material should not be used to produce academic papers, student reports, or other documents. Since a lot of viewers of our channel are completely new to ROS2, we are going to spend a significant amount of time explaining all the steps. So let's start with the prerequisites. To implement the material presented in this tutorial, you need to have Linux Ubuntu 24.04. Do not use Windows Subsystem for Linux or WSL since you might have issues displaying graphics. Install Linux Ubuntu on a computer. If you have a Windows computer, then you can install Linux Ubuntu in parallel to the Windows operating system by using a dual boot approach. To verify that you have the correct Linux Ubuntu version, open a terminal, that is, click here and search for terminal, and then in this terminal type this command. This command is going to list the current Linux Ubuntu version. Then you need to have a ROS2 Jazzy Jalisco installed on your system. If you don't have a ROS2 Jazzy Jalisco, then go on our YouTube page and search how to install ROS2 Jazzy on Linux Ubuntu. There are several tutorials. After installing ROS2 Jazzy Jalisco, let's verify that you have the correct ROS2 version and that you have properly installed ROS2 Jazzy. First of all, let's run this command to list the content of the standard installation folder for ROS2 Jazzy Jalisco. And if you see something like this, then most likely ROS2 Jazzy is installed. However, let's perform additional verifications. First of all, let's try to source, or better to say, to execute this setup.bash script file. This file will set the ROS2 underlay, that is, it's going to set all the parameters and run the scripts that will enable you to run ROS2 on your computer. And then let's print this environment variable, and if you see as the output Jazzy, then this means that ROS2 Jazzy is properly installed on your system. The next step is to install Gazebo and all the necessary packages. Here, let's start everything from scratch and let's open a new terminal. And remember, every time you want to play with ROS2 in a terminal, you have to source the environment. That is, you need to execute this command. Okay. The next step is to install Gazebo. However, before installing Gazebo, make sure that you run these two commands that are compressed as a single command. First of all, this command will update the local package list on your system, and the second command will actually upgrade all the packages. So press enter, enter your password, and be patient. It might take even several minutes to execute this command, depending on how often you update your system. To install Gazebo Harmonic, which is the recommended version for ROS2 Jazzy, you need to execute this command. And then, as you can see over here, ROS2 2 Gazebo is installed on my system. However, in your case, this command will take a while to execute, maybe even 5 minutes. Now, let's verify that Gazebo is properly installed. For that purpose, you need to source the base ROS2 environment once again, such that the packages are updated, that is, that the list is updated. And then let's first run this command, which is going to list the installation folder for Gazebo, okay? And then at the end, let us try to run the Gazebo simulation by simply typing gzsim, and then let's see what will happen. This window should open, so let's start one of these simulations. For example, let's start Panda joint control window, let's press run, and over here, after some time, a robot should show up. Okay, so let's wait, here it is, and then let's try to run this simulation by simply playing this button, and then over here you can move the robot. Good. This means that Gazebo is properly installed on your system. And let's continue further. Let's close this window, let's press Ctrl C, and there we are. The next step is to install the necessary packages. First of all, let's install ROS2 Jazzy joint state publisher. Then let's install joint state publisher GUI. Then let's install ROS Jazzy Zacro. Then let's install this set of packages for Gazebo. And then finally let's install this package that will enable us to use functions for doing coordinate transforms in Python. Let us print the list of all Gazebo related packages. To do that, simply run this command and you should see something like this. If you see something similar to this, this means that all the packages are there. Note over here that these are the most important packages. Okay, the next step is to run the differential drive robot simulation. As explained previously, we have created a separate video tutorial explaining how to implement a differential drive robot from scratch. If you want to learn how to do that, then watch that video tutorial. On the other hand, in this video tutorial, we are going to use a shortcut. That is, we are going to use a built-in differential drive robot simulation that comes with this package, ROS Gazebo Sim Demo. So let's close this window. Let's again open a new window such that we start completely from scratch. And then over here, let's source the environment. And then let's run this command. Let's explain what's happening over here. Here, we are calling ROS2 launch. That is, we want to run a Python launch file. Then we specify the name of the package. Here is the package that contains the Gazebo simulation of differential drive robot, and here is the name of the file. And if I press enter, you'll see first of all this RViz window will appear. We are going to use this RViz window to track the odometry, that is to track the motion, and here's the Gazebo simulation of a differential drive robot. As you can see over here, there are two robots. There is a blue or purple robot and there is a green robot. You can control any of these robots. In this video tutorial, we are going to control the blue robot. However, before we explain further, let's look briefly into this Python file and let's see what's happening here behind the scenes. First of all, we need to locate this file. This file is located inside of this folder. So let's now just copy the path of this folder. Then let's go back to Nautilus, or you can simply type here Explorer to start File Explorer or Nautilus, and then click here. That is enter the path of this folder. You can see where we are. We are inside opt ROS Jazzy. This is the standard folder for Jazzy Jalisco. Then we are in the share folder, and then we are in the side of the package folder and inside of the launch folder. And we need to find the correct Python file and just to see what's happening inside. However, if you're not sure about the name, go back here and see the name of the file we just launched. It's called diff drive launch. So let's start to try to find it. Here it is. Do the right click, open with text editor, and you can see what's happening over here. This is a standard Python launch file. In fact, on the YouTube tutorial, on my YouTube channel, there are a number of tutorials explaining how to write Python launch files. Here we are obviously not writing from scratch this file. However, we are still trying to figure out what's happening behind the scene in our simulation. First important thing to note is the name of the source file. This is a diff drive file. Then over here you can see the nodes that are being started. It's the RViz node. Then we are starting this ROS Gazebo bridge node, and this is a very important node. This node is used to establish a communication link between ROS2 and Gazebo. That is, we are using this node behind the scenes to bridge ROS2 and Gazebo topics, and you can see how the bridge is written, which is very instructive, and you can see at the end what is being launched: RViz and bridge, and few and G as sim. That is our model. Simple as that. So let's close this window and let's continue further. The next step is to obtain more information about this simulation. To obtain this information, we need to open a new terminal. So click here. And then in this new terminal, again, we need to source the environment. Keep in mind that this terminal that is currently running the Gazebo simulation should be active, and it should stay active until the end of this video tutorial. Next, let's investigate the topics that are running behind the scenes. So let's type ROS2 topic list and let's analyze what's written. We can see these 4 important topics. First of all, we can see vehicle blue and vehicle green. For every vehicle, there are 2 topics. This first topic, command velocity, is used to send command velocities. That is, this topic is used to send control action, and the second topic, called odometry, is used to read the odometry information from our robot. That is, to read the position, orientation, and velocities from our robot. And you have these 2 topics for both. The next step is to investigate the type of messages that should be sent through these topics. Let's start with this topic over here. So let's copy the topic name and let's type ROS2 topic info, and then let's paste the name of the topic. And we can see very important information. We can see that the type of message is twist. Twist contains information about linear and angular velocity. However, let us assume that we don't know that and that we want to find what is inside of the twist message. To do that, we need to use this command, ROS2 interface show. So let's type this, and then let's type this message type. Let me paste this, and let me make space over here. And let's see what's happening. And very important information is displayed. This message expresses velocity in free space broken into its linear and angular parts. We can see the linear vector and angular vector of velocities, and we can see that both of these vectors have 3 components, since in general we live in 3-dimensional space. Very nice. Let's talk about other topics and let's see what these topics are. So let's again type ROS2 topic list, and let's focus on this odometry topic. Let's copy its name, and then let's repeat everything. So let's type ROS2 topic info, and then let's paste this name. And we can see that the type of the message being sent through this topic is navigation message odometry. So let's copy this name, and then let's type ROS2 interface show, and then let's paste this message type, and you can see this very useful information about this particular topic, or better to say message. This represents an estimate of a position velocity in free space. That is, odometry provides us information about position, orientation, and velocity. Not only position and velocity. This is very important to keep in mind. Okay, and then we can see over here what we have. We have the header field. The header field obviously contains a timestamp as well as the frame ID. Then we are also keeping track of the child frame ID. We are not going to use this header since we are going to manually track the time in our code. And here comes a very important part. The second field is the pose field. And the pose field consists of additional fields. We have the pose as well as the covariance. We are not going to use covariance. However, inside of the pose, we have position and orientation. That is, the pose, which is a part of our odometry message, will contain information about the position of the robot and the orientation of the robot. So if we go back and we look at the graph of the robot, odometry will give us information about x and y and theta. And this is very important. As you will see later on, theta is not going to be expressed as an angle. Theta is going to be expressed as a geometrical object called quaternion, and later on we will have to extract theta from the quaternion description. This will be explained later on in the code. So let's continue and analyze what is another component of our odometry. The last component is the message of the type twist with the covariance. That is, odometry will also provide us a twist message. That is, it will provide us the linear and angular velocity. We are not going to use this twist message. Excellent. And let's continue further. The next step is to create ROS2 Python package and node for controlling the position. Here we need to perform the following steps. First of all, we need to start a new terminal, source the environment, and create a workspace folder. Then we need to create an empty package folder structure, then required files. Then we need to implement the source file. Then we need to modify the package XML and setup.py files. So let's do that. For that purpose, let's open a new terminal. And let's first of all create an underlay. That is, let's source the setup.bash file. Next, let's create the workspace and source folders. First of all, go to the home folder, and then inside of the home folder, create a folder called pospy.ws, which is our base workspace folder, and inside of that folder, create the source folder. And then let's navigate to the source folder by executing this command, and inside of this folder we are going to create our empty package. To create the empty package, we need to execute this command. That is, we need to type ROS2 package create, then we need to specify the build type, which is AIM and Python, and then we need to specify the name of the package. The name of the package is pospy package. Let's press enter. And now if you type this command, you will see new folder whose name is the same as the package folder. So let's navigate to this folder over here, and you can see several files. The package XML, setup CFG, and setup.py are configuration files. At the end of this tutorial, we will have to modify package.xml and setup.py file if we want to run our code. Then we have this folder, pospy package. This folder will contain the source file for controlling the robot, and then you have resource and test folder, which are not being used in this video tutorial. So let's start with implementation of our control algorithm. The control algorithm, or better to say its source file, should be placed inside of this folder. So let's now navigate to this folder, and if you now type this, you will see that there is a single file. We need to create a new file that will implement our controller. However, before we implement the controller, let's look at the big picture. That is, let's explain the working principle of our controller. For that purpose, I created this detailed manual which has 1, 2, 3, 4 pages, and this manual explains the derivation of the position controller. And let's go over this derivation, since it's very important to understand the fundamentals of the position controller before you actually implement it. Consider this illustration. As I explained previously, this illustration shows a mobile robot. Here you can see the mobile robot body, you can see the left wheel, you can see the right wheel, you can see the center of the robot body represented by the point B. First, let's introduce coordinate systems, also known as coordinate frames or simply frames in the robotics literature. Let the center of the robot body be denoted by the point B as mentioned previously. At the same time, this point is the origin of a body coordinate system B, or the body frame. This is very important to keep in mind. That is, the point B is the origin of the body frame. The axes of these body frames are XB and YB. This coordinate system or coordinate frame is fixed to the robot body and moves together with the robot. In addition to the body coordinate system, we also have a base coordinate system whose origin is denoted by the point O. This is a fixed coordinate system with the fixed axis denoted by X and Y. The center of the robot body B has coordinates X and Y in the base coordinate system X and Y. This is very, very important to keep in mind. That is, we have two coordinate systems or coordinate frames. We have the body coordinate system with the axis XB and YB, and this body coordinate system is fixed to the robot and moves as the robot translates and rotates. On the other hand, we have a fixed coordinate system with the origin O and the axis X and B. We are expressing the position of the point B with its coordinates in this coordinate system. Let's talk about the orientation. The orientation of the base coordinate system with respect to the body coordinate system is described by the rotation angle theta, however you like to denote it. As the robot rotates, the angle theta changes. The angle theta is the angle of the that the coordinate axis XB creates with respect to the coordinate axis of the fixed frame OXY. That is, that it creates with the axis X, or better to say, the angle theta is the angle between this line here that's parallel to the axis X and the axis XB. Let the desired position of the center of the robot body be denoted by the point D. This point has coordinates XD, YD in the coordinate system X, O, Y. This point is selected by the user, and this is the final destination of the robot. That is, we want to steer the robot to this position. The coordinates of this point in the base coordinate system are XD and YD as explained previously. The control objective is to move the center of the robot body B to the point D. Here, we are not explicitly controlling the orientation angle theta of the robot. That is, we do not care what will be the orientation of the robot at the desired position D. We are just interested in steering the robot to the desired position. The control method presented in the sequel can be easily modified such that we control the orientation at the desired position or the desired orientation at the desired position D. For example, we can first move the robot to the position D, and then we can adjust the orientation in this point. Consider this geometry and this triangle. At any time instant, the robot can only move along the direction of the robot body coordinate axis XB. That is, the robot can only move along the direction of XB at the fixed time instant. That is, if we freeze the time instant, the velocity vector will be along XB. The velocity vector here is represented by VB. This is very important to keep in mind. This velocity, that is the velocity VB, is called as the linear velocity vector. We assume that we can control the linear velocity vb. Also, we assume that we can control the angular velocity of the robot body. Since the orientation angle of the robot body is denoted by theta, the angular velocity of the robot body is denoted by theta dot, where the dot notation is used to denote the first derivative. To summarize, we assume that both the linear velocity vb and the angular velocity theta dot of the robot can be controlled. The position controller should compute these values, and then these values are sent to the local controller that should move the robot and produce these velocities. Here, we assume that the local controller is infinitely fast. In our case, the local controller is a differential drive controller, which is implemented by Gazebo plugin. And again, the assumption is that the local controller is infinitely fast and that the dynamics of the system can respond with zero delay. In fact, Gazebo simulation has dynamics incorporated, and the controller cannot respond infinitely fast. That is, the differential drive controller, since it's moving a mass, will have certain transient period. However, in the derivation of the control algorithm, we are not taking this into account. Of course, this is an abstraction and simplification that is often not met in practice, as it is the case in our simulation and as it is in the case of real life system. However, since this is an intro tutorial mainly focused on the position controller or kinematics controller for presentation clarity, we will stick to these assumptions. So let's see now what happens under these assumptions. Let me now zoom out this and let's see. Under the assumption that the coordinates of the point B are known, that is, under the assumption that the position of the point B is known, from simple trigonometry we have this formula. We have that the tan of the angle theta d, you can see how the theta d angle is constructed, is simply yd minus x, so you can see like this, so let's just be careful, yd minus y over xd minus x. That is this length of the triangle over this length of the triangle, and that gives you the tan of the angle theta d. The angle theta d is a very important angle and is referred to as the desired orientation angle. This angle is the angle that the line connecting the points B and D creates with the x-axis of the base coordinate system O. Then, from the previous equation, we have the theta d expressed in radian is a tan 2 of the argument yd minus y divided by xd minus x, where a tan 2 is the two-argument arctangent function. That is, by knowing the current robot position expressed by x and y, we can compute the desired orientation angle theta d at any time instant. Now, the natural question is, why do we use a tan 2? Well, there is a difference between a tan and a tan 2. A tan 2 is a smarter version of arctangent function. When I say a smarter version, I mean the following. A simple arctan function cannot figure out the quadrant in which our angle is. However, the a tan 2 function can do that. That is, a tan function can, for example, return the correct value if the theta d angle is from 90 to 180 degrees or from minus 90 to minus 180 degrees. And a tan 2 will return the correct number. On the other hand, a tan function will not do that. That's the main reason why we are using a tan 2. The significance of the desired angle comes from the following facts, namely, if the orientation of the robot theta is equal to theta d, that is, if this angle theta is equal to theta d, then the robot moves along the line, or better to say along the straight line connecting the point B and D. That is, the robot is approaching the point D. Consequently, our controller has to ensure that the orientation angle theta approaches the desired orientation angle theta d. Consequently, the simplest controller for steering the orientation angle to desired orientation is given by this equation. That is, we simply take the difference between theta d and theta. This is the orientation angle error. We multiply this by constant, and we say that the set point value, or the control signal in the form of the angular velocity, is equal to that value. That is, the control signal in the form of the angular velocity is simply proportional to the orientation error. Keep in mind this. K theta is the controller parameter selected by the user. Note over here that we are using a proportional controller. However, everything explained in this tutorial can be generalized to PID or even some other more complex controllers. The control signal theta c is sent to the local controller, and the local controller should produce this angular velocity. That is, the control signal theta c is the set point or desired value for theta dot. Note over here that theta c is not actually equal to theta dot, since in reality the dynamics is not infinitely fast, and basically you cannot make any angle to be equal to desired values infinitely fast, because you have the dynamics. After some transient period, we can say that theta c dot becomes theta dot. So keep in mind that thing. Let us analyze this equation. So let's see what happens. Let me now expand this so we can see both equation and we can analyze it from here. So what happens? When theta d is different from theta, that is when this term is non-zero, then theta c dot is different from 0 and the control actions are generated and sent. What does it mean? If you look now at this graph, this means that the robot will kind of have some angular velocity that will tend to make theta to be equal to theta d. That is, we're going to move the robot in the direction of this line. So somehow the motion is going to look like this. We are going to converge to this straight line. And this is because we are always penalizing the difference between theta d and theta. When theta d is equal to theta, theta c dot becomes 0, and we are moving along the straight line. So we don't need to make any adjustments for the angular velocity. Now, ideally, this difference, that is the difference between theta d and theta, should be very small. Ideally, if the controller is properly designed, this difference should asymptotically approach 0. If that is the case, then the asymptotic stability of the closed loop system is achieved. Next, let us explain how we are going to control VB. The principle is very similar, and let's explain this principle. So what's the idea over here? Let's look at the graph. Here, since we measure position x and y, and since we know xd and yd, we can compute the distance from B to D. And this distance is given by this equation. Obviously, we are using the Pythagoras theorem, and we can always compute the distance between current point and the desired point. And we can simply derive the controller that will depend on this distance. Namely, we can take this distance, we can multiply it by some proportional constant kv, and we can obtain the expression for the desired velocity vc. That is, vc in this equation is the control signal in the form of the linear velocity, and kv is the controller parameter selected by the user. The control signal Vc is sent to the local controller and serves as the set point for the velocity Vb. Again, since you're dealing with dynamical system, Vc will only approach Vb. You cannot make a system that is infinitely fast since you have dynamics. That is, in general case, Vc is a set point for Vb, where Vb is the actual velocity. Keep in mind that. Now let's analyze this equation and let's see what's happening. When this distance BD is small, then the value of VB is small and V decrease the velocity. If this distance is equal to 0, this means that we have arrived at this position and we shouldn't move from this position. Consequently, the velocity VB should be equal to 0, and that's the main idea. The further away we are from the point D, the value of the velocity VB is larger. And note over here that we have implemented a proportional controller for VC. You can easily introduce the integral controller or even derivative controller that will make a transient response more smoother, or you can have a better transient response. And finally, let's now summarize the equations for calculating the control values. We have three equations. First of all, we assume that x and y are measured. Then, since we know y d and x d, we can actually compute theta d, which is our desired steering angle. Once we know the desired steering angle, we can compute the set point for the angular velocity by using this equation, and we can compute the set point for the linear velocity. And we do this at every time instant t. That is, every time we receive sensor information, we compute this equation, then we compute theta c and vc, and then finally we send these set points to the local controller, that is to our differential drive controller, that will actually figure out how to move the wheels such that these set points are being enforced. And that's it. Simple as that. The next step is to write the Python code that will implement the control algorithm. For that purpose, you need to be in this folder. Now, here you have several options. You can, for example, use a built-in nano editor, or you can use your favorite coding editor. In my case, I'm going to use Visual Studio Code. If you want to follow my path, that is, if you want to use Visual Studio Code, then you need to install it. Go to my YouTube page and search for Install Visual Studio Code on Linux Ubuntu. There are several tutorials. To start Visual Studio Code, I will simply type this, and here it is. Let's create a new file. The file is created by clicking File, New File, and I'm going to call the file as demo.py. Make sure that you save this file inside of this folder. To show you the correct path, this is the package folder. Then click over here and save the file as demo.py. Here, to save time, I'm simply going to copy and paste the content of the file, and I'm going to explain this file line by line. So let's do that. Okay, here it is. Let me now minimize this and let's see. First of all, you need to import RCLPY. RCLPY is the ROS2 client library for Python that is included with any standard installation of ROS2 distribution. RCLPY provides with a standard application programming interface or API such that you can use ROS2 functions, modules, and classes inside of the Python development environment. Then you need to import the node class. We are importing the node class from rclpy.node. Node class is the main class of RCLPY that implements the basic ROS2 node functionality. The idea over here is to use the object-oriented approach. Namely, the base node class can be considered as a template, and this template contains the basic functionality. It contains functions for creating timers, callback functions, subscribers, publishers, and then the idea is to define our own class that will inherit from this base node class, and this will be explained later on in this tutorial. Next, we need to import the class that is used to define the twist geometry message. We define it like this. So what is a twist message? As explained previously, twist is a class, or better to say message, containing components of the linear and angular velocity vectors that are used to control the 2D mobile robot. If I now go back and look into my equations and into my graph, the twist message will be used to send the set points for VB and the set points for theta dot. This will be explained later on in the sequel. Next, we need to import the odometry class. Note over here from where we are importing. And just as a side note, navigation message, geometry message are standard ROS2 packages. That is, from these libraries or modules, we are importing twist and odometry. Odometry is a class or a data structure, or better to say, a message containing information about position, orientation, and velocities of the robot. As mentioned previously, we are going to control the position and orientation. We are not going to, not here, I have to be careful and I have to restate this. As mentioned previously, our feedback control algorithm is going to receive information about position and orientation and not information about the actual velocities of the robot. That is, position and orientation correspond to x, y, and theta. And for that purpose, we are going to use the odometry message. And this odometry message will be received from the Gazebo simulation. Then over here from TF transformations, which is actually a ROS2 package, we are importing Euler from Quaternion. This function is used to transform the orientation expressed in Quaternion form to the Euler form. That is, this function is used to retrieve this angle theta, or orientation of the robot, from the Quaternion object. Next, we need to define topic 1 and topic 2. Topic 1 is used to send the control messages. As we have seen previously, here is the name of the topic. And topic 2 is used to receive back information about odometry, that is, to receive back from Gazebo simulation of our mobile robot information about position and orientation of our robot. Then we need to track time and we need to import math since we are using math functions. Here is the class that implements our controller. We are typing class, then the name of the class, and over here we are saying that our class is inherited from the base node class. Then here is our constructor. The constructor receives several parameters specified by the user. XDU and YDU are the coordinates of desired or the target point. If I look at the graph, these are the coordinates XD and YD. Then this constructor receives information about control parameters or proportional control parameters, that is information about KV, and K theta U. Note over here that the U index means specified by the user. So if you look back at the controller implementation, that is, if you look at this equation, at these three equations, K theta and KV are actually KV and K theta, and that's it. And XD and YD are given over here. Next, inside of the constructor of our child class, we need to call the constructor of our base node class, and we need to specify the controller name or the node name. I'm going to simply call it as controller node. Then over here, I need to store inside of my class, that is inside of its private member variable, the coordinates set by the user. Then I need to store my control parameters. Then I need to instantiate and store messages. First of all, a message which I called last received message for storing odometry. Then I need to store initial time by calling this constructor. Then I need to store last received message time. This is the time corresponding to the last received message. Then I need to store, always in my class, the control message we are sending. So let me briefly explain what's happening here. Last received message will be continuously be updated on the basis of odometry information. On the other hand, the control velocity message is of the type twist, and this is the message that our controller function will calculate. Then I need to specify and set them to 0 components of the linear velocity vector, namely my twist data structure or class has linear and angular velocity components, and I set them to 0, as well as I set to 0 angular velocity components. That's it. Next, I need to create, or better to say, to instantiate the control publisher. The purpose of the control publisher is to periodically send control messages, that is to send control velocities. To do that, I need to call the function create publisher. Note over here that this is actually a function of my base class, that is of my node class. Keep in mind that. So what I need to specify in order to define a publisher, I need to specify a message type that we are sending. It's a twist message. I need to specify a topic name over which we are sending. Obviously, here is the topic name, and that's the topic name we extracted from the terminal. And then I need to specify this buffer size. Then I need to define my subscriber, right? The principle is the same. I'm calling create subscription function of the base node class. I'm specifying the type of messages that I need to receive from my sensor. They're of the type of odometry. Then I need to specify the topic name. Here's the topic name used to communicate the odometry messages. Then over here I need to specify one very important function. This is a callback function. And namely, every time there is a message on the odometry topic, we're going to call the sensor callback function. And here is the buffer size for storing messages. Next, we need to define a timer. That is, the publisher needs to have some information, or precise information to be correct, about how often we want to send messages. And for that purpose, we need to define a timer. First of all, we need to specify the period of the timer. The period is the period of sending control messages. Since this period is 0.250, this means that we are sending a message every 250 milliseconds. Note over here that the unit is millisecond, and consequently we will send 4 messages per second. And over here we create a timer. We simply call the function create timer, we specify period, and we specify the control function, and that's it. Next, we need to implement the sensor callback function, and we need to implement the control function. So here is our sensor callback function. As mentioned previously, the sensor callback function is being called by our subscriber every time there is something on a topic. What do? We provide to this callback function a message, and we simply store that message in the last received message, and we record the time of the last received message. And here comes the most important function. Here is the control function. To remind you, this control function is related to the control publisher. Here it is, and related to the timer. In fact, the callback function, control function, is associated with the timer, and it's being called every period. So let's see what's happening. First of all, from the stored last received messages, we're extracting XC and YC. That is, we're extracting the current position and orientation. If I go back to my equations, I'm extracting X and Y. In my code, X and Y are denoted by XC and YC. Then I need to extract the quaternion from the message. Namely, my odometry message contains information about the orientation of my robot. That is, it contains indirect information about this angle theta over here. However, this information is not in the angle form, it's in the quaternion form. A quaternion is a mathematical object similar to a vector, although it's a 4-dimensional vector, and it contains information about the instantaneous axis of rotation and the angle of rotation. So I need to extract the quaternion. Quaternion has 4 components. I'm extracting x, y, z, and w components. And then I'm providing this list with the components of the quaternions to the function Euler from quaternion. This function will calculate roll, pitch, and yaw angles. That is, it will calculate the Euler angles. Note over here that I'm in 2-dimensional space and my angle is only yaw. This is actually theta. So in our case, yaw is actually theta, and consequently we can extract theta. Note over here that I denote theta as theta c. Here is theta. In the code it is theta c, where c denotes the current, and the same applies to x and y. Then we are calculating the desired orientation, and let me now do this so you can see the code. I can do it like this, right? Let me do it like this such that you can see it better, and let's start here. So the code line 135 implements the equation number 6. Nothing special. Then the code line 137, here this code line actually implements the line 8. And finally the code line 138 implements the code line number 7. Simple as that. That is, this code line, here it is, then we have 137 is the equation 8, and then we have 138, this is equation 7. And once I do that, I need to create my control velocity message. Note over here that I'm only filling in the x components. This is because the velocity is always in the x direction of the axis of the body coordinate system. This is determined by the kinematics of our mobile robot. Then I'm specifying y and z components of the linear velocity are zeros, and I'm specifying x and y components of the angular velocity to be 0, and only the z component of the angular velocity is non-zero, and it's equal to theta velocity. That is, x velocity and theta velocities are being stored in the linear.x and angular.z respectively. Here's one important comment about the z-axis. The z-axis, let me bring the graph. The z-axis is the z-axis of the body coordinate system, and this z-axis is oriented toward us. You don't see it over here, since you will only see a circle with a dot. That is, you will see the top of the arrow, and theta dot is actually the component projected on that axis. So keep in mind that when implementing the code. And then finally we are sending the control command, and we are simply publishing over here the message. That is, we are simply sending the message, and we are printing the message with by retrieving the time, and over here we print the message. Okay, so this is our implementation, and here's the main function. So what's happening in the main function? Before using the RCLPY, we need to call the init function, and this is where we do it. Then we need to select the control parameters. Here is the value for kVu and k theta u. Here you can, for example, increase a little bit for the linear velocity. However, keep k theta u as it is. If you increase these values, the controller might become a little bit unstable. So there is some tuning phase that I will not explain in this video tutorial due to the brevity. However, you can experiment as you wish. Here we are setting the desired coordinates. That is, we are setting the coordinates of the point xd and yd. They are denoted by xdu and ydu. And then over here we are creating the node, or better to say instantiating node. We are starting a node by calling the spin function, and the code will run over here. The code continuously runs until the user presses Ctrl+C, then we are destroying the node and we are shutting down everything. And here's our entry point. That is, if you're running this from a terminal, the main function will be executed first. And that's it. Let's save this file and let's continue further. Now, the next step is to edit the configuration file. So click on File, click on Open File, go back to this folder and open these two files. First of all, click on package.xml, and over here we need to specify the dependencies. So what are the dependencies? Obviously, our package depends on several things. First of all, it's going to depend on everything imported over here. So it needs to depend on RCLPY, geometry message, navigation message, and TF transformations. Consequently, we need to set these dependencies as well as some other dependencies. To set the dependencies, we need to add these lines. Here they are. Here, first of all, we are setting RCLPY, then we are setting geometry messages, then we are setting the navigation messages, and then we are setting as a dependency TF transformations. Okay, so let's save this file and let's proceed with the setup.py file. Over here in the setup.py file, locate the section called entry points. Inside of the entry point, there is a field called console script or the key console script. And here we need to add these lines. First I will add the lines and then I will explain the purpose. It's actually a single line. Here it is. And let's explain what's happening. The entry point is the name of our executable. Here the executable will be publisher. And we are going to run the code by simply typing ROS2 run and the name, which is simply publisher. When we write something like that, the system will look inside of the pos.py package, that is inside of the package we have created. Then it's going to look into the file demo.py, that is, it's going to look in this file, and then over here it's written main. This means that we are going to execute the main function. That is, whenever we write from the terminal ROS2 publisher or ROS2 run publisher, we are actually running inside of the package called pos.py package. Inside of the demo script, we are running the main function. Simple as that. That's it. So let's save this file and let's continue further. Now we have modified the package.xml and setup.py file, and we can proceed further with final steps. As the final step, we need to verify that everything is properly installed. But before we do that, let's navigate several steps back until we go to our base workspace folder. Note over here that whenever you want to build a package, you need to go to this base workspace folder, not the base package folder, but instead to the base workspace folder. And inside of this base workspace folder, we need to install a ROS2. ROS2 is a very nice tool that enables us to verify that all the dependencies are properly installed on our ROS2 system before we build everything. This will help us to eliminate any compilation errors. So let's initialize and let's update ROS2. Okay, and finally, let's again make sure that we are in the base workspace folder, and then let's run this command to make sure that all the dependencies are there. And you should get the message, all required ROS2 installed successfully. And then finally, let's build everything. To build everything, you simply need to type this. Colcon build, package select, and the name of the package, and let's press enter. And here's the summary, no errors. And finally, we can run the control algorithm node. To do that, open a new terminal by clicking over here. Now, before opening the new terminal, you have to make sure that the simulation is. So find the terminal in which the original Gazebo simulation is running. It should be active. And click here. You should see this RViz window and you should see the simulation over here. So let's do the following. So let's now rearrange these screens so we can follow what's happening. I'm going to click here, zoom in this arrow to show you and explain what this arrow is. This arrow is actually the initial pose of this left robot over here. Now I'm going to go here, okay, so you can see what's happening, and then in this newest terminal, or open a new terminal if you didn't do so, you need to first of all source the environment. However, here you're executing not the base environment source command, instead you are actually executing this command. You're executing postpy ws install setup.bash. That is, you're sourcing the setup.bash from your created package. So run this, and then finally you can run the executable, and the executable can be executed or run like this. So you're simply typing ROS2 run, name of the package, name of the executable, and if you go now back to our setup.py, you can see what will be executed. Inside of the demo.py file, the main function will be executed. Okay, so let's do this. And now let's change the screen here. And then let's press enter and let's see what's happening. Now, 1, 2, 3, bang. And you can see how a robot is moving. You can see on RViz how its orientation is being changed. You can see that the pose is being changed. That is, we are approaching the position, and the position should be somewhere here in the corner, 15 meters or something like this. Yes, here it is. Note over here that the controller is very slow, and this is deliberately being done since I want to improve the stability of the control algorithm, and you can of course increase the speed of response of the control algorithm by changing these constants. And that's it. That's all for today, and thanks for watching.